Hi, I'm Bruce Rouse, and welcome to this course on Energy Fundamentals for Energy Engineers. This course introduces you to those energy and physics fundamentals that are important for energy engineers. You'll start by learning how to apply the first law of thermodynamics to identify savings opportunities that may not otherwise be obvious. The course then looks at the energy-related characteristics of water and air, followed by the characteristics of fuels. Electricity is discussed in some detail, covering its characteristics, AC power, DC power, losses in cables, and the electrical section then concludes with AC voltage and equipment efficiency. A section on heat transfer is then presented, and finally the course looks at an easy-to-make mistake and how to avoid it. Now, to get the most from this course, I suggest that you do the exercises during the lessons. Often you'll be asked to think about an issue and put your response into the comment box. Also, complete the assessments, which will help you gauge your learning. You can skip lessons if you feel knowledgeable about particular topics, but please try to complete all the assessments, which are mandatory if you wish to get certified. Your best friend, the first law of thermodynamics. The first law of thermodynamics states that energy cannot be created or destroyed. It can only change form. You can apply this law to identify energy losses and thus potential energy savings opportunities. Do this by identifying the form of energy that is useful. Let's call this the useful energy service, and then trace its path back to the input energy, the energy used. Or, alternatively, you can trace a path from the energy input through to the useful energy service. What proportion of energy input ends up as useful energy? Can energy losses be reduced? And by the way, this leads to a very useful definition of energy efficiency. Energy efficiency equals useful energy service divided by the input energy. Let's illustrate this with an example. Light. The useful energy service provided by light is the illumination of objects. For general tasks involving writing or reading, the amount of useful illumination that needs to be provided is approximately 300 lux. For work involving fine detail, for example, tailoring or assembly of small parts, around 600 lux is required. For simple navigation, 40 lux is sufficient. Now, for areas that are illuminated by electric lighting rather than the sun, the energy input is the amount of energy supplied to the light source. Some common light sources include fluorescent tubes, they're gradually becoming less common, and LED lamps, gradually becoming more and more common. Now, please pause the video now and draw a diagram showing energy input into a light above a desk, and then the useful illumination provided to the person using the desk. For example, using a laptop computer on the desk. Then show all the losses along the way. Now, feel free to do an internet search to help you with this exercise if you don't understand much about lighting. Put your responses into the comment box. Okay, well done. You may have ended up with something like this. Now, by the way, the name of this diagram is called a Sankey diagram. In the class resources is a link to the tool I've used to make this diagram. So we have electricity coming into the lamp, which is 100% of the energy supply. Then of that 100%, about 15% of that is being converted into light by the LED light source, which is about 100 lumens per watt, let's say. And then let's say about 85% is going out as heat. Of this 15%, that's coming out as light, then let's say that about 80% is useful light out of the fixture. And then the other 20% is light that's bouncing around in the fixture. It's not really providing anything really useful. And that's just converted to heat, basically. So the light output ratio, or the LOR of this fixture, is then 80%. And then of the light coming out of the fixture, let's say that roughly 60% is illuminating the surfaces that you're using, near the desk where you're working, the laptop itself, and so on. And then let's say about 40% is illuminating areas not being used. For example, some of them will be going down off the desk onto the floor. You're not really using that. Maybe some of it's going behind the desk itself. You're not really using that. Some of it's going to the sides. So there we can see in doing this diagram, we can trace the useful energy input down to the useful light output. And you can see the efficiency actually is pretty poor. Now, undertaking this simple exercise has identified two broad areas of wastage and potential efficiency improvement. By using the first law of thermodynamics and building this diagram, firstly, you can see that there's a lot of wastage in the light source. An LED light that produced 200 lumens per watt would double the amount of useful light. Secondly, and this is often neglected by those without much experience in lighting, there is quite a bit of wastage in the way the light produced by the light source is directed to where it provides useful illumination. And that would be even worse if, let's say, that desk was being illuminated by a fluorescent tube that was lighting the whole room and not just the work area. Let's now look at another example. An electric pump on a farm drawing water out of a dam and supplying water to fruit trees. What is the useful energy provided by the pump? It's the transfer of water from the dam to the roots of the plant. So what is the energy input? Well, it's the electrical energy provided to the pump. A Sankey diagram could show something like this. We've got electricity into the pump, 100% into the pump motor. Then the pump motor itself, the shaft power is about 93% with 7% losses. Then let's say the pump efficiency is around about 65%. So of the shaft power into the pump, the useful efficiency going to pumping water is actually 65%, the rest is heat. Then let's say the water is then delivered to the roots. 40% of the water actually delivered to the plant goes to the roots, and then the rest of the water is lost, it evaporates or it goes on leaves, etc. So many engineers will look at a pump and their first thought will be a more efficient motor. But by preparing a Sankey diagram, you can see that there are opportunities that could give much larger savings. The overall system is only 7% efficient. Looking at this diagram, you can start to see that energy efficiency opportunities could include using sensing so as to not over-irrigate, using a drip irrigation system rather than a spray irrigation system to reduce water loss from runoff and evaporation, pumping slower to reduce the pipe friction losses, and changing to a more efficient pump. And then finally, looking at a more efficient motor. It should be possible to save both energy and water. So I suggest that you practice what we've covered in this lesson. Think of an energy using system you are working with and trace it through from the input energy through to the useful energy service. See what inefficiencies and losses you can identify and possible ways of addressing them. I suggest you do this before moving on to the next lesson. Introduction to energy calculations. A fundamental skill any energy engineer should have is the ability to undertake the calculations needed to determine energy usage. But what is energy? Let's look at two fundamental definitions. Energy equals work done. The basic System International or SI unit of energy is the joule. A joule is the work done by a force of 1 Newton acting through 1 meter. Now the second definition actually is an energy, but sometimes people confuse it. It's called power. Now, power is the rate of use of energy or the rate of doing work. The base SI unit of energy is the watt, and it corresponds to 1 joule of energy being used over 1 second. In practice for electrical energy, the common units are kilowatt hours, equal to 3,600,000 joules, and megawatt hours, which would be 1,000 kilowatt hours. For fuels, energy may be expressed in megajoules or gigajoules, or possibly in kilowatt hours. In relation to energy associated with the mass of an object, the potential energy is the mass of the object times the gravitational constant of 9.81 meters per second squared times the height. With respect to the movement of mass, kinetic energy equals half of the mass times the velocity squared. Undertaking energy calculations involves understanding the characteristics of the object that the energy is acting on. If you can identify the relevant characteristics, you are well on the way to being able to calculate anything. For example, pumps are commonly used to pump water. So it's important then that you are familiar with the characteristics of water, such as its density, that can be used when calculating energy use. And you should also know about friction and energy losses that occur when water moves through pipes. Fans are usually used to move air. So if you are doing fan calculations, it's important that you understand the characteristics of air. A heating, ventilation, air conditioning system, or HVAC system, may use chilled water to supply water to a coil through which air is blown to provide cool air. To understand energy flows through this system, you would need to know the characteristics of water for when it's pumped and when it's cooled, and the characteristics of air when it's cooled and when it's moved by fans. In subsequent lessons, we're going to look at characteristics of common energy sources, after first looking at the characteristics of water and air. Before moving on to these, here is a quick test of your knowledge. 1 cubic meter of water is pumped up to a height of 100 meters. How much energy is used to pump the water, assuming a pumping system with 0 energy wastage or losses? This is a theoretical question. Clearly 0 energy wastage or losses is impossible. Okay, just pause the video, answer this question. Okay, did you get 0.273 kilowatt hours or 273 watt hours or 0.981 megajoules? Here is the work solution. We have a water volume of 1 cubic meter and a water density of 1,000 kilograms per cubic meter. That gives a water weight of 1,000 kilograms. The gravitational constant is 9.81 meters per second squared. The height is 100 meters. The change in potential energy equals mgh, and that comes out to 981,000 kilograms per meter squared per second squared, which equals a joule. So therefore the energy required is 981,000 joules or 0.981 megajoules. We divide by 3.6 to convert megajoules to kilowatt hours, which gives us a required energy of 0.273 kilowatt hours. Now note that in order to answer that question, you need to know the density of water, their characteristics. You should also be able to convert between units. If you can't remember the conversion, an internet search will quickly give you the answer. This might be particularly the case if you have a mixture of SI units and non-SI units, for example, BTUs or megajoules. Let's see you in the next lesson. Characteristics of water. Water is commonly used to transfer heat energy, and the characteristics of water that are important to energy calculations include those characteristics that define how much heat it can transfer and also how much energy it takes to move water. Now, as we learned in the previous lesson, the density of liquid water is around about 1,000 kilograms per cubic meter. When we think of water, we typically think of it being in a liquid form. To raise the temperature of 1 kilogram of water by 1 degree Kelvin takes around 4.18 kilojoules. This is known as the specific heat of water. If you are doing work associated with HVAC systems that use chilled water or heating hot water, this is a very important number to know. Consider, for example, water with a flow rate of 7.2 meters cubed per hour being cooled from 12 degrees to 7 degrees by a chiller. What is the chiller useful output power? Knowing the density and specific heat of water, the amount of cooling energy provided by the chiller can be calculated by using the formula rate of heat transfer equals the mass flow rate times the specific heat, or CP, times the change in temperature. The calculation steps are shown in this table. Here we have the water flow rate of 7.2 meters cubed per hour, a water density of 1,000 kilograms per cubic meter, and there's 3,600 seconds in an hour. Combining those numbers, we get a water mass flow rate of 2 kilograms per second. The temperature in is 12 degrees Celsius. The temperature out is 5 degrees Celsius. That gives a delta T of 7 degrees Celsius or 7 degrees Kelvin. The specific heat of water, the CP, is 4.18 kilojoules per kilogram Kelvin. The chiller output power is the mass flow rate times the CP times the delta T, which comes out to 58.5 kilojoules per second or 58.5 kilowatts. Now, the phase change of water from a liquid to a solid when freezing it, or from a liquid to a gas when water evaporates, requires a lot of energy. The latent heat of fusion of water, the heat when freezing at a temperature of 0 degrees Celsius, is 334 kilojoules per kilogram. The latent heat of vaporization of water when boiled at 100 degrees Celsius at sea level at atmospheric pressure is 2,256 kilojoules per kilogram. This latent heat of vaporization of water is also important when it comes to understanding the properties of air and when undertaking calculations involving air conditioning. Water doesn't have to be boiled at 100 degrees Celsius to change from a liquid state to a gaseous state. It can also evaporate at much lower temperatures and be absorbed into the air. Air always carries some water in it. The amount of water that is held in air is determined by the vapor pressure of water. As air warms up, it can hold more water. As it cools, once the air temperature reaches water saturation temperature, water in the air will begin to condense out. Energy engineers should thoroughly understand the properties of water. The resources section of this lesson includes links to additional information. Characteristics of air. The properties of air are important to energy engineers when it comes to HVAC system calculations and human comfort. Air is predominantly comprised of nitrogen, then oxygen, water, argon, and carbon dioxide. The water content of air varies with temperature, air pressure, and relative humidity. For a given air pressure, the characteristics of air change in a non-linear fashion depending on its temperature and relative humidity. The psychometric chart is a useful visual way of understanding these characteristics. If you know, for example, the temperature and relative humidity of air supplied to a HVAC system, the leaving temperature and humidity, so let's say it's going into a heating or cooling coil, and the air flow rate, You can then use the psychometric chart to identify the amount of energy that has been transferred to the air. In this lesson, I'm not going to explain how to use the psychometric chart. There are many other useful YouTube videos and websites that do this. Refer to the resources section of this lesson to access these resources. If you're working with HVAC systems, you should be able to undertake calculations using the psychometric chart. If you don't know how to calculate, for example, the energy required to chill air with 70% humidity at a dry bulb temperature of 35 degrees Celsius down to say 15 degrees Celsius, then you should thoroughly review these additional resources. Characteristics of fuels and combustion. Many facilities directly combust fuels, which may be solid, such as coal, liquid, such as heating oil, or in a gaseous form, such as natural gas. To understand the amount of heat generated during combustion, you need to know the heating value of the fuel and its mass flow rate. And you usually assume that perfect combustion occurs with no excess air. So the heating power provided equals the fuel mass flow rate times the heating value. When perfect combustion occurs, the byproducts of the combustion process are carbon dioxide and water. With imperfect combustion, other products such as carbon monoxide and nitrous oxides might form due to insufficient oxygen. On the other hand, if excess air is provided to ensure perfect combustion, energy is lost in unnecessarily heating the air that goes through the burner but isn't used in combustion. As a byproduct of combustion is always water, the amount of heat delivered depends on whether that water is fully or partially condensed or not condensed at all. If it's fully or partially condensed, that will increase the amount of heat that is provided, as is the case in a condensing flue hot water boiler. A fuel's lower heating value, or LHV, assumes that the water doesn't condense. It's calculated based on the fuel and air being supplied at 25 degrees Celsius and the combustion products or exhaust being at 150 degrees Celsius. The higher heating value, or HHV of a fuel, assumes that all the byproducts of combustion, particularly water, condense and that the final temperature is also 25 degrees Celsius. Now, some manufacturers of condensing flue boilers claim an efficiency of greater than 100%. This is, of course, impossible based on the first law of thermodynamics. When claiming this, they have used the LHV, or the lower heating value, when calculating the energy input. In a condensing flue boiler, the amount of useful heat out is somewhere between the LHV and the HHV, depending on the temperature of the exhaust gases and the extent to which combustion is perfect and the amount of excess air is low. On fuel bills, the heating value of a fuel may be stated. Convention is for fuel suppliers to usually use the HHV. It makes their fuel look more potent. And you've guessed it, suppliers of equipment that use fuel usually use the LHV, as it makes their equipment look more efficient. So which heating value should you use? The LHV or the HHV? Given that fuel suppliers generally use HHV, good practice would be to use the HHV, as it then matches with utility bills. Make sure that you state in your report that HHV has been used. The resources section of this lesson includes a link to published heating values for some fuels. Now, note that as the chemical composition of fuels varies from place to place and from time to time, it's always best practice to seek out the heating values published by the company which apply the fuel to the site at the time of supply. Finally, remember that heating values are based on the mass or weight of the fuel. If you are using natural gas or another gaseous fuel, which is often metered by volume, you will need to take into account the pressure and temperature of the gas at the meter. As gases are compressible, you need to know both the temperature and pressure in order to calculate the density and thus the energy content. Now, some gas meters have inbuilt pressure and temperature compensation and show the volume delivered at standard temperature and pressure, or STP. And the gas supplier will often provide a heating value based on volume at STP. It's important to know if your meter is STP compensated or not, and if not, that you take this into account when calculating the volume that would be at STP. Electricity and its characteristics. To start this lesson, I need to explain an invisible characteristic of electricity that you should never, ever forget. What do you think that is? Electricity is dangerous. Very dangerous. With fuels, the danger is visible. We've all seen movies of cars exploding after a crash when its fuel ignites. All of us have, at some time, had a minor burn associated with heat from a fuel. For example, we've been burnt by a gas stove, or we've been burnt by a fire. Just a small burn, but we've all had some sort of burn, and so we naturally respect these fuels and know that they're dangerous. But the danger associated with electricity is not as visible, and therefore electricity may not get the respect and caution its usage merits. So that you better appreciate just how dangerous electricity is, pause this video now, go to the resources section of this lesson, and watch the short video illustrating what could happen if care is not taken with electricity. A word of warning, you may find this video distressing. Because electricity is dangerous, any work done in an electrical installation should be done with the power supplying that installation turned off and it verified or tested that the power is actually off. You can do an entire engineering degree focused on electricity. That's an electrical engineering degree. So clearly in this lesson, I'm just going to be dusting the topic. I would urge you to learn more if you don't know much about electricity using the links in the resources section. Now, any electrical circuit is defined by its voltage and its current. Voltage, or potential difference, can be thought of as the pressure that is trying to push the electrons through the electrical circuit. The higher the voltage, the higher the pressure. Current is analogous to the number of electrons that are being moved by the voltage. The higher the current, the greater the number of electrons that are being moved. The power, measured in watts, delivered by an electrical circuit at any instant is the voltage measured in volts at that instant multiplied by the current measured in amperes, or amps for short, at that instant. From an energy efficiency perspective, we are interested in electrical power, and because of this, it's important to better understand the relationship between voltage, current, and power in alternating circuits. From an energy efficiency perspective, we are interested in electrical power, and because of this, it's important to better understand the relationship between voltage, current, and power in alternating current circuits. We'll look at this in the next lesson. AC power. Grid electricity is supplied as alternating current, or AC. In an AC circuit, both the voltage and the current are continually changing and changing in direction, following a repeating pattern. The frequency at which this pattern repeats, this sine wave pattern repeats, is either 50 Hz or 60 Hz, depending on which country you are in.
I'm going to use this spreadsheet to explain alternating current power and power factor. Alternating current power is where we have a current which alternates around zero. So here this graph here, there's a red and blue line here, they're in sync. One is the current, the other is the voltage, and they're oscillating around about this zero position using a sine wave pattern. So this is a pure sine wave. It would be a very clean circuit. In reality, often you'll have little bumps in these sine waves. They're called harmonics. I'm not going to go into detail in harmonics in this lesson, but you should be aware of them. So we have the so this is over a full rotation of a machine there, then there's a second rotation. So alternating current is typically generated by rotating machines, and so we have this waveform here, and you can see it's a sine wave, and in this case the voltage and the current, if you look closely, that's kind of a blue and a red line. The red line is the current, the blue is the voltage. Now when they get out of sync or slightly out of phase, and I'm just going to change the phase angle here slightly, I'll make that 25 degrees so we can see that in this case we have the current is leading the voltage is lagging slightly behind. Now this can occur in electrical circuits when we have what we call inductive or capacitive loads. There can be a shift between the phase of the current and the voltage. They're still both at 50s at the frequency, which is either 50 or 60 cycles per second, but they're slightly moved out of phase. And if I change that, say to say a 50 degree angle, you can see that they move out of phase more and more. Okay. Now the power, if I just go back to that 0 point, power is the instantaneous multiplication of voltage times current. So right here the current is 1.414, the voltage 1.414, you multiply those two together and we get a power there of 2. Now when we're talking about AC power or AC voltage or AC current, we take the square root of the mean of the squared values. So that you see this waveform here, that line there of 1 is actually representing the square root of the mean of the voltage and the current. And it's also actually the mean of the power. The power here is just the voltage multiplied by the current. So as the voltage and current drop down to 0, the power drops down to 0 there, then it climbs back up as the voltage and current become negative. A negative number times a negative number is a positive number, so therefore we've got that power there staying current. And the RMS power is 1, as is the RMS voltage and RMS current, as shown here. Now, when I change the that phase angle, we can see here that these are getting out of sync, and now our power waveform is slightly different. It's actually going into negative power at some points when either the current is negative and the voltage is, and the other is positive, or vice versa. And we can see here that the true power has actually changed. It's actually dropped from below 1. While our voltage and current remain at this remains at 1, the true power RMS has dropped to 0.87. And so in actual fact the amount of useful power we're getting has dropped due to this phase difference. So this is basically power factor. When the power factor is 1, there is no phase difference and we're getting the maximum amount of power. Once we change that phase angle, and that could be caused by what's called an inductive load, which is involving a transformer or something similar, or a motor is essentially a type of transformer. We have, or a capacitor, they get out of phase and we get a bad power factor. And the worse the change in angle, so if I go to 60 here, so they're 60 degrees out of phase, our power factor here drops to 0.5, which is very, that's a bad power factor. So basically the useful power is the sum of the instantaneous volt amps, which here we can see is 0.5 watts, with a power factor of 0.5. And so we're getting a lot of useless power. Another analogy of describing this is what we call the beer analogy, is where you're getting a glass of beer, and in this case half of it is beer, half of it is just the foam on top, which is, you haven't really bought that. You're getting something that you don't want. You've paid for a glass of beer and you've got all this froth on top, which you don't want. Now this here is what we call the power triangle, and it just shows the relationship between the true power, the apparent power, which here, and the reactive power. So when we have a power factor of 1, which corresponds to a phase angle of 0, there's 0 reactive power. As that power factor deteriorates, we get a more reactive power. And this line here, voltamps is remaining current. So that's the RMS voltage times the RMS current. But the true power is actually dropping. So this is what you will call the power factor. And basically that angle there, we call phi, the angle between there and there, and the power factor is cos phi. It's another name for the power factor. So look, this spreadsheet is available with the lesson. You can have a play with it and just see how, in different cases you can get, well, it's the power factor of 0. We're getting 0 power. I don't know if that's theoretically possible, but I certainly have seen cases where the power factor has been as low as 0.5, which is a very bad power factor. So have a play with this and you will get a better appreciation of power factor and how that relates to the phase difference between voltage and current.
For an AC circuit, the root mean squared power measured over one cycle is the RMS voltage times the RMS current times the power factor, RMS being the root mean square. Where the electrical loads at a site are such that the site has a poor power factor, electrical currents increase above what they would be were the power factor to be 1 or close to 1. This both increases loading on switchboards, and it also means that the current your electricity grid needs to supply is higher than it would be otherwise. For a site which is supplied with electricity on a kVA tariff, from the perspective of managing electricity costs, it's important to try to keep the power factor as close to 1 as possible. Keeping the power factor close to 1 will also minimize loads on switchboards. AC power is well suited to powering electric motors. The speed of the motor is proportional to the frequency of the AC waveform. For a 3-phase induction motor, 3 different lines, each carrying an alternating current, at a phase angle of 120 degrees different from the other 2 phases. Loads are either connected in a star or delta connection, noting that in a delta circuit there is no neutral connection. The power delivered to a 3-phase load is equal to 3 times the line to neutral voltage times the line to neutral current. However, as the voltage for 3-phase power is often given as the line to line voltage, the formula for 3-phase power then changes. 3-phase power equals the square root of 3 times the line to line voltage times the line current times the power factor. DC power. Many electrical devices use DC power. Can you think of some? Yes. Items such as computers and LED lights use DC power. Also, solar photovoltaic panels produce DC power. The ubiquitous phone chargers convert AC power to DC power. DC, or direct current power, has a constant voltage. With a DC circuit, you don't need to worry about power factor. Power equals volts times current for a DC circuit. However, whilst you may think that AC power is the most common form of power, the use of DC power is more prevalent than you might think. Variable speed drives, otherwise known as variable frequency drives, VSDs or VFDs, often used with induction motors, take the fixed frequency AC supply, rectify that to DC power, then invert it back to a variable frequency AC power. Electronically commutated permanent magnet motors, or EC motors, used in applications such as plug fans, are supplied with AC power, but rectify that to a DC power source, which is then controlled with power electronics to provide high efficiency over a wide range of speeds. Your washing machine probably has a permanent magnet motor in it. As the conversion of AC power to DC power results in losses, and with the growing use of rooftop solar PV systems which produce DC power, there is potential for small efficiency gains by running entire sections of a building or facility entirely on DC power. It's not commonplace yet, but from the perspective of resource efficiency, it's an attractive idea. Losses in electricity transmission and distribution. According to Ohm's law, voltage equals current times resistance. As power equals voltage times current, the power losses in a circuit due to its resistance can be expressed as power loss in watts equals the current squared times the resistance. This is why transmission cables run at such high voltages, potentially several hundreds of thousands of volts. By running at very high voltages, the current required to deliver power is reduced, and thus the power losses, which are proportional to the square of current, are much lower in the cables. It also means that smaller cables can be used than would otherwise be the case. For electrical cables, the resistance of a cable is proportional to its length and its cross-sectional area. If I double the voltage of any electrical circuit, I can deliver the same amount of power with half the current and 1/4 of the power loss due to cable resistance. I would have to increase cable cross-sectional area 4 times or double the cable diameter to reduce the power losses due to cable resistance if the voltage wasn't doubled. Now, whilst an understanding of this is usually to the periphery of the work done by an energy auditor, it is important when understanding the electricity transmission and distribution network and the important role that transformers play in enabling the efficient transmission of electricity. Nonetheless, despite the efficiency of running high voltages, it's fairly typical for losses of around 10% to occur between centralized electricity generation and users in an electrical network due to both resistance losses in cables and losses in transformers. As the use of rooftop solar becomes more important, just to appreciate how the high DC voltages, and solar systems are running higher and higher voltages, how these voltages, higher voltages, can reduce cable size and thus the cost of the solar system, whilst also reducing resistance losses. AC voltage and equipment efficiency. Equipment designed for use with AC power is designed to operate at a specific voltage. When the voltage is different to the design voltage, this may impact on the efficiency of the operation of the equipment. This is particularly the case with induction motors. It is also the case with high-intensity discharge lighting, including fluorescent lighting. The link in the resources section shows the impact of varying voltage on three-phase motors and how high-efficiency motors respond in a different way to low-efficiency motors. As over-voltage decreases efficiency, there is a strong argument for ensuring that supply voltages match the requirements of the equipment on site. Voltages in any electrical network vary quite a lot. Energy auditors should pay attention to voltage. It can be easily and safely measured with plug-in power monitors that plug into a wall socket. It may be the case that where a site has sustained and significant overvoltages, there is opportunity to save energy by reducing voltages. This would be the case, for example, if fixed-speed induction motors comprised a significant proportion of the load. If the site has a dedicated distribution transformer supplying it, it may be possible to request the tapping of the transformer be changed in order to lower the voltage. Alternatively, a dedicated voltage optimization unit could also be installed. As many countries move to more distributed energy resources, such as rooftop solar, management of voltages in distribution networks becomes more challenging. Possibly we're going to see an emergence of network-controlled dynamic voltage. Possibly we're going to see an emergence of networks dynamically controlling the voltages, which ideally would result in more consumers getting electricity supplied at the nominal voltage rather than above, as it now can often happen. Heat transfer. An understanding of heat from a first principles perspective is useful for energy auditors to understand heat loss or gain, human comfort, and opportunities to save energy. Heat can be transferred through 4 different mechanisms. Can you name them? Pause the video and have a go in the comment box. The 4 heat transfer mechanisms are conduction, convection, radiation, and evaporation or condensation. Rather than provide detailed advice on calculating these, you can find that information in the resources section. I am going to provide a brief explanation of each, and then discuss where each is relevant. Conduction. Conduction is the heat conducted from the hotter substance or the hotter body to the lower body, or the lower substance. The rate of heat transfer is in linear proportion to the temperature difference. Bulk insulation in ceiling space or in walls is a retrofit measure that will reduce the conduction of heat. Convection is actually a specific form of conduction relating to gases and liquids. Convection is the movement of a gas or liquid, and it can increase heat transfer rates to or from the gas or liquid and the surfaces it is touching. Convection is linked to conduction. The movement of air across a surface will increase the rate of heat transfer across the surface. Radiation. This is what enables life on our planet. Heat always transfers from the hottest surface to the coolest surface, but not in a linear fashion. Rather, the rate of heat transfer is related to the 4th power of the temperature of a surface. But it's also related to the emissivity of a surface, which is why shiny foils are often used on the outside of the lagging of hot water pipes. It's to reduce the radiant heat transfer from those hot pipes. Once you appreciate the power of radiant heat transfer, you'll have a greater understanding of the advantages and disadvantages of thermal mass in buildings. For example, I've lived in buildings in both hot and cold climates with high amounts of thermal mass. A wall which remains stubbornly hot or stubbornly cold decreases comfort due to the continuous radiant heat or cold that wall projects. On the other hand, when that wall is at a comfortable temperature, it increases comfort by counteracting unpleasant air temperatures. Evaporation and condensation. This is particularly related to heat transfer in air. When water evaporates or condenses, a lot of heat is transferred. It's why evaporative cooling can be so effective, and why air movement in a hot climate can make it feel cooler than it really is by increasing the rate of evaporation from skin. To wrap up this lesson on heat transfer, I also want to draw your attention to the second law of thermodynamics, which indicates that in regards to temperature, there is irreversibility in natural processes, where heat always flows from the hotter body to the colder body, and never from the colder body to the hotter body. How to avoid the easy to make mistake even the smartest auditors sometimes make. Energy efficiency calculations can be complex, and even the smartest engineers can make mistakes in the units used in calculations. For example, by confusing energy with power, that is, confusing kilowatt hours or megajoules, the amount of energy used over a certain time period, with kilowatts or megajoules per hour. That is the load, power, or rate of use of energy. You'd be surprised how often even experienced auditors who, when in a hurry, can confuse kilowatts and kilowatt hours and end up with errors in their calculations. So, how do you avoid this easy to make mistake? What do you think? Pause the video and write your answer in the comment box. All you need to do to avoid this easy to make mistake and to avoid embarrassing yourself and possibly ending up with some wildly inaccurate conclusions is to always, and I mean always, take your time to write down the units that apply to any number you use in a calculation. And in your final answer, apply the same arithmetic to the units that you did to the numbers. So for example, let's say you are calculating the energy used by a fixed speed fan over 1 day. You would lay out the calculation as shown in the slide. You have the motor nameplate power, you write down the quantity of 10, and then you write down the units next to it, kilowatts. The estimated load factor, taking into account motor efficiency, that would be 0.7. That's dimensionless, or you could write 70%. The hours per day is 8 hours. The energy, which is the nameplate power times the load factor times the hours per day, is 56, and then we just multiply down those units on the right to get kilowatt hours per day. By clearly writing down and spelling out the units, even down to the time period over which the energy use has been calculated, it's almost impossible to make a mistake in your calculation and get the units confused. In line with this, I also advise making unit conversions explicit. For example, let's look at a situation where we know the natural gas flow rate supplied to a boiler in meters cubed per hour. Let's assume the boiler has an efficiency of 80% and we want to know the boiler output power in kilowatts. By making all the units explicit, it's hard to come up with the wrong answer. Here we have the gas flow rate of 10 meters cubed per hour at standard temperature and pressure. We have a gas calorific value of, say, 38 megajoules per meter cubed. That gives us a gas boiler input of 380 megajoules per hour, multiplying out those units. You can see the meters cubed cancels out when I multiply them. The efficiency is 80%. The heat output is therefore 380 times 80% equals 304 megajoules per hour, writing down the units. The megajoules to kilowatt hour conversion is 3.6 megajoules per kilowatt hour. So we divide the 304 megajoules per hour divided by 3.6 megajoules per kilowatt hour, gives us an answer of 84 kilowatt hours per hour, or 84 kilowatts. If you are unsure how to convert between different units, do a web search. Now, if you aren't already doing so, go to your calculation spreadsheets and add a column to include the units of measurement. It takes very little time to avoid writing down the units and can help you avoid making silly mistakes. Energy Fundamentals course summary. This short course has provided an introduction to energy fundamentals for energy engineers. You've learned about the first law of thermodynamics and how useful it can be to identifying energy efficiency opportunities. You've learnt the basis of various energy calculations and the characteristics of water and air as they relate to energy. You've then developed an understanding of how to calculate heating power provided by fuels, then looked at various aspects of electricity and its characteristics. Then we've covered heat transfer and finished up with a reminder to always write down units when doing calculations. As a result of this, you now have a grounding in energy fundamentals of key importance when looking for and quantifying energy efficiency opportunities. I look forward to seeing you in the next lesson or the next course in this Energy Auditor series. Thanks. Congratulations on completing this course. You'll find in this additional bonus lesson a PDF summarizing the content of the course, along with links to additional learning resources. But now that you've gone through the whole course, do you really know the topic? And how can you prove that you know it? Anyone can watch a series of videos, but does that mean that you have any expertise? In today's world, does anyone now just trust a certificate of completion? This is why at the Sustainability Education Academy, we have developed a comprehensive assessment process for each of our courses. Once you pass all the assessment activities in the course, you are issued with a certificate of competence that lists the competencies that you've achieved. The value of the Sustainability Education Academy certificates can be seen in the recognition of them by a range of professional associations, including the Institute of Electrical and Electronic Engineers, or IEEE, the Australian Institute of Refrigeration, Air Conditioning and Heating, or AIRA, and the Energy Services and Technology Association, ESTA. So now, if you're keen to show that you know it, I've got something special for you. A coupon which reduces the costs of the certification assessment. Go across to the Sustainability Education Academy using the link at the end of this lesson and apply the coupon code at the checkout. This will then give you access to this same course, but on the Sustainability Education Academy platform, and access to the assessment quizzes, which you can't access here on Udemy. Pass all those quizzes and you'll get that certificate of competency. All the best.